we are going to be talking about timing planes and IP production. Now this might sound a little drab, but it's really not. It's one of the most important topics that we have in IP video to deal with today, is how to get different pieces of media content properly synchronized, and how do we allow enough time in our processing chains for all these things to work together. So joining us is Andy Rayner, who's the Chief Technologist for Nevion, division of Sony.
Thanks, Wes. Good to be with you. In case you haven't guessed, I'm from the UK. It's a pleasure to be here. I've just about synchronized my timing plane to West Coast USA now. So what I want to do is talk about the challenges of timing in IP production, what the current status is, what we actually really want to achieve and haven't yet, what the solution is looking like in the work that we're doing, and then a call to arms, because it's a chance for you guys to be involved in this as well. So there's a whole load of standards that actually have conspired together, or converged together, probably is a better word, to create 2110 at the end there. And that's been a lot of work in a lot of different spheres that have actually contributed to that. And all of those have created a very workable ecosystem, and there is now a whole suite of 2110 standards, and then some complementary control plane standards from NMOS, which actually make up the suite of tools which we're actually using for IP production now. And this is really maturing now. This is becoming business as usual. But the reality is that in the future, we're actually moving more and more to a soft environment. So there are some challenges on timing that actually come up as we move to that environment. And my watch is telling me it doesn't understand what I'm saying, which is always a challenge. But one of the things that I think I was slightly naive about as we worked through 2110, building the standards, which we didn't possibly think through as a system-wide thing, because very much ST2110 is all about interface standards, standards of interfaces rather than system-wide standards. And what we defined was the performance of interfaces and how you handle signals. But one of the challenges we have, the beauty of ST2110, is that it's essence-based. So we actually handle the audio as a separate flow. It can be routed through the infrastructure that needs to process audio. Same happens with a video, and the same happens with other video in different ways and with metadata in other ways. But there comes a time where we actually need to bring them all back together again. So we need to create our composite flow, which actually has all of those signals time-aligned and creating one complete system. And the challenge we have with the current ecosystem is that doesn't happen automatically. We actually, in the way most solutions are being developed, we actually lose the origination time that's actually inherently been created in the sampling of the video and the audio. That's lost as we go through processing devices en route. And that means we've got no way of knowing at the far end what the actual accumulated relative timing is in each video and audio and metadata essence that we're trying to reconcile. Now, we did look at this in the 2110 revisions that have just happened. So -10 of 2110 is what we call system and timing. And that actually, we've added in a few hooks in the revision of 2110 to allow us to define one or two extra parameters, and we will look at those now. So it's entirely possible, and it was already entirely possible, for a device in a 21 chain to be what we call a preserver, i.e. the video frame that comes in with timestamp N could be egressed with timestamp N as well. That's entirely possible. In fact, in our portfolio, we have some products that are actually doing that. But there wasn't a definition of a device declaring that. So we have actually added the option for a device to actually declare that it's a preserver of time. So if you think about this, I have my timestamp, my origination time, as I propagate through a device. If it preserves the origination time, so the original sampling time of video frame in, then it can declare that. And that actually allows us to ripple origination time through the system. However, it's inevitable that some devices do not do that. And I won't go into the real details on this screen, but you can actually look at those later. Let's look at that in a real-world scenario, what that actually means in a real-world scenario. This is a relatively complex syndicated production scenario, such as you would have for a large international event or large national event, drawn up by my friend Prin to actually help illustrate this point as we're actually working here. The key thing is, what you have is, if you like, your origination time sampling that happens with the cameras and microphones on the left here. So that's capturing a moment in time, and the PTP locked RTP timestamp actually references all of those. What happens then is, as we ripple through the production, we're inherently creating new timing planes. So the first one is likely to be the egress for the vision mixer. Now, in a traditional SDI world with modern vision switches, that probably would only be 1 or 2 lines of a new timing plane. Unfortunately, the way a lot of people are implementing 2110, that actually tends to be a frame later, because people are scared about TR offset, which I haven't got time to talk about now. But so everyone quantizes it to the next frame boundary. So what we actually have already got is we've got a new timing plane on the egress of that video router, that video mixer. There's actually possibly 1 frame later. But what we then are saying, if that's a host production and we syndicate that into unilateral productions downstream, then that vision mixer is effectively concatenated with the presentation mixer for the next thing. So that's in itself is going to take a new timing plane. But what happens if we're actually taking some ISOs from some of those host cameras directly into our vision mixer? This is a relatively simple example, and it's a relatively trivial one because we're only talking probably about a 1 frame delay here, but it illustrates the point, because the timing plane of this camera here coming into my second vision mixer is actually 1 frame in advance of the program out that I'm actually trying to work with. That actually can become more complex, and I'll talk about another couple of options in there. So this is a simpler diagram to show the same concept here. So we've got feeds being used in multiple timing planes downstream. This diagram hopefully represents like a plethora of timing planes that could exist due to either equipment latency or intentional creative delay that we're adding in for different reasons. And let me explain them. These aren't supposed to illustrate a specific timeline, but they're supposed to actually illustrate different elements of latency that could exist. So we talked about the event production switcher there. That's possibly going to be, in a 2110 world, currently a 1 frame delay there. We're talking about a presentation switcher, maybe another 1 frame delay. If we've got remote control surfaces where someone's actually doing, got a remote compressed mosaic, and they're actually doing a TD roll from their dining room, as many people have done in the last 2 years for COVID, that actually could be the order of half a second by the time we've actually got a compressed proxy out and coming back in. So we've got a different timing plane. They're living in a different timing plane. We've then got, typically even worse, remote international commentary. You know, we create, again, a proxy video. We send that typically over public internet, so we need to do some buffering to someone in another country doing a remote commentary. We're pulling back in. So that could be maybe in excess of 1 second, maybe even 2 seconds, a new timing plane we've created that actually exists for that. And of course, that may be variable. We've then got things like profanity delays, which are typically intentionally added. That's a creative decision to create that new timing plane, and that has to be the order of a few seconds to allow people to react. Then we've actually got things that are unavoidable latencies due to the way processing works. So as people have introduced augmented and virtual reality into sets, those typically take many frames of processing to actually do VR. So you actually have an example, when we'll come on to this next. I'm just going to talk about this next. This is a real-world example that from someone I was talking to only a few months ago, where we've actually got effectively a VR system that has a 200 millisecond latency. So we've got some cameras on the set that are actually going through the VR system, and we've got other cameras that are not going through the VR. So we've actually got effectively a 200 millisecond timing offset between the stuff that's gone through VR and stuff that hasn't, and we're actually looking, we need to reconcile that. Now, this is all talking about very deterministic things. So if you've got an appliance, we talked about the vision switcher that maybe has a 1 frame delay in a 2110 world. We're moving into a world where there's a lot of software processing. Now, the beauty of software is it works very fast. Typically, it works much faster than real time in the processing it does, but you're not interested in the fastest it can do it. You're actually interested in the longest time the software will take to instantiate something. So as we are continuing to move from an FPGA centric world where everything is a few clock cycles and we can nail that to the nanosecond, software processes, we need to know the longest time that software process is going to take to actually complete that function before we can actually add that into our timing process. So it becomes a more challenging model because that actual execution time is non-deterministic. But the same model that I talked to, or the same challenge exists when these are virtual functions as to whether they're appliances with deterministic transit. But what we then have is this processing time element here is actually something that's very difficult to articulate, and we actually have to bound that worst case area that's on the graph. Now, before we got into 2110, we inherited that to give credit, the audio guys with AES67 did stuff first. So they actually fought some of the battles, and some elements of what we're talking about here are covered in the way AES67 does link offset. That doesn't actually cater for the actual processing, but it actually caters for everything else about how the data's handling. And the concept that it has is you define a presentation time that actually is safe with respect to the latencies in the system, which includes the propagation delay. So you actually create a link offset, which is a time that you can comfortably present your audio at that is going to work. So going back to that software model, we've actually got a number of virtualized processing functions, and we actually, for each of those, we need to actually consider the worst case time, so the longest time. But similarly, we also have to allow for the shortest time as well. And if you want to listen back to John Mayart talking on the previous presentation, he talks a little bit about that as well. I'm not going to jump into this one too much, but just to say, in the timing planes, as we go between locations, we inherently have a phase shift, so there is always going to be some time. You could say within a plant, the latency is negligible, but as we're starting to do more and more distributed production, then we have many milliseconds of latency. Now we're likely to be frequency locked, so we don't have wander, but we will actually have static phase offset, which we need to compensate, and that effectively becomes another timing plane. I think I've talked already about this concept about proxy remote production, which is similar to remote panel production, where you actually are making decisions in a different timing plane, and you're actually bringing that information back and hopefully applying it into a buffered signal so they still apply. So the question is, as we do time alignment, there you go. As we're doing time alignment, how accurate do we need the time to be? Okay, so the question is, how much do we want to line up? So if you're purely interested in achieving lip sync, reasonable lip sync, you can say, as long as we're aligned to within 5 milliseconds, maybe, I'm comfortable with that as a process. However, AES67, 2110-30, a subset of AES67, is quite possible for you in an ecosystem, and I know some people that do it, to actually route each individual audio as a mono signal. Now, if you're doing that and you've got phase coherent audio that you're straddling across individual separate IP flows, then you've got to be better than 20 microseconds, assuming we're in a 48 kilohertz world, to actually be guaranteed that you're sample accurate in the realignment. So suddenly the game becomes a lot more challenging in terms of the alignment you want to achieve. Personally, if I have phase coherent audio, I want to carry it in a bundle that's actually all of those channels together. And then there's the absolute time delivery. When how accurate does my system need to be for my final presentation side that you saw on the graph there? So these are actually different requirements, but in the work we're looking at, we're actually aiming to make sure we're better than phase sample audio alignment in the work we're doing, in the way which we bring this together. So what's what we're working on? This is becoming ST211011. That's the work package. We've only had 3 meetings on it yet, so this is just underway. But effectively what we're doing is a hybrid model. So as I've said, it's entirely possible now for devices to declare they are a time preserver. And in the utopia view is that each device actually propagates origination time, and then you don't have to do anything, because at this point you look at the relative timestamps on the flows and you could actually make that decision. You don't need to do anything. The reality is, especially with the audio world not having that flexibility, we actually need a hybrid system. So we need to be able to allow for that time preservation to actually happen and the time to ripple, but we also need a control system to be able to provide the coordination and actually compute in, if you like, do the math that aggregates the processing times in the systems that are not preservers, that don't declare that. So what we're working on is an ecosystem that has something like this. That control system can also be configured to understand what you're looking to add in for profanity delays, etc. So all of those other variables, creative variables we're adding in, are actually in there as well. So effectively what we have is the devices are actually providing the requisite information, and then the control system is providing that coordination. This bottom bit is probably not going to be out of the tin, because not all devices, in fact probably very few, yet provide everything we need there. But we're looking to get to the point where there is a specification there. So it is entirely possible at a system level for by using time preservation and the declaration of the relevant chains to actually do that. So this was the original specification on -11 that we put together, that we put into SMPTE 3 or 4 months ago. So this is the automatic reconciliation of media essence. So that's the dream. It's going to take a while to get there. So what can we do about this? What I would really love, because we want to make this as catch-all as possible, as I'd love some more user stories. So if anyone has got scenarios they can think of where I say, I bet you haven't allowed for this kind of setup. So I'd love any of those gotchas. So if you want to send me in something, then I'd love to have an email from you and talk to me afterwards, so we can actually try and make sure we build as many of those user stories in as we try and refine what we're doing here. So hopefully that's given you a bit of a view of where we're heading. Watch this space. If you fancy a decent cup of tea, then do come and catch me at some point. Thank you very much. Hopefully that's been of some value and has got your brains ticking away. Does anyone have any questions?
So resolving the difference between the video and the audio in that last slide you showed would involve intentional, perhaps dynamic delay in the production program output, right?
Absolutely. So the question is, on the dynamics, what you don't want to do is to actually have a varying, like, program out time plane, do you? So you really want to be able to compute the worst case egress timing plane that you need to actually construct to allow for the variability of the components within it. Now, there are some bits that you may not be able to predict there, so you may not be able to get that right. There are lots of things that are very deterministic. So all of the appliances, in most of the appliances in the current system, including a lot of the compute, the VR, AR systems, we know it's 5 frames or it's 10 frames or whatever it is, and so we can allow for that as a worst case. There are some variable stuff. So if we think about that remote commentary thing coming in, that round loop of the proxy going over public internet, buffering, commenting, coming back in, that time plane, has to be tracked, and that could be something that's dynamic. But what we need to do, and there's a similar process in the software world, is we have to construct the worst case timing plane that we think is safe. So you allow a margin for that. You construct that, and then you need to do requisite buffering of those essences as they arrive at that point to actually align them back into that back into that timing plane. And the principles in a software cloud environment are very, very similar. The method of tracking time is going to be different, but the actual principles of what you're trying to achieve are similar.
Okay. Mr. Rayner, thank you very much. Appreciate it.